So in the last lecture, we have shown that compactness, sequential compactness, and limit point compactness are equivalent for metric spaces. And in this lecture, we will continue our discussion about compactness and sequential compactness, but now in arbitrary topological spaces. And we will show in particular that compactness does not imply sequential compactness in general, and also that sequential compactness does not imply compactness in general. And to prove these two, well, we will give like examples of both cases. So we will show that first of all that there exists a compact set which is not sequentially compact, and for the second one we will show that there exists a sequential compact space which is not compact. And to show that to show both these properties, we will use some of the theorems that we have already shown, like the Tikhonov's theorem and the equivalence of all these kinds of compactness properties in metric spaces. So first of all, let me give an example of a space which is compact but which is not sequentially compact. And due to the time constraint, I will not be able to give all the details of the proofs, and I will leave some either some ideas as an exercise, or I'll give a reference in for example in Munkras's book, where the statement is proved, and you can go and check it. If you have any questions, feel free to ask me, and I'll try to clear your doubts. So let us start with an example of a compact space which is not sequentially compact. So in this example, we take X. Well, first of all, let us take an index set, because we will form an arbitrary Cartesian product. So for the index set, we will take J to be the unit interval 0, 1, and for each alpha in J, we let X alpha to be the same unit interval with the standard topology, with the subspace topology from the in R. And of course, by the Heine-Borel theorem, we know that each X alpha is compact for all alpha. And now we will form the product space X, which is the arbitrary Cartesian product of all these alphas, and we will endow it with the product topology. So each X alpha gets the subspace topology in R, and X gets the product topology as an arbitrary Cartesian product. Now Tikhonov's theorem implies that X is compact, because we have given it the product topology and each of the X alphas are compact. Therefore Tikhonov's theorem says that such an arbitrary Cartesian product with the product topology is compact when each of these X alphas are compact. So this is a compact space, and we will prove that X is not sequentially compact. X is not sequentially compact. And to show this, we will construct a sequence in X, say Xn, such that no subsequence of this sequence Xn converges. Okay, so this will imply that X is not sequentially compact. And to do this, we will use the following lemma. And this lemma says that if Xn converges to some point X in in a product space, say in X, which is the product of X alpha. This is now for general product spaces. So with the product topology, X alpha can be arbitrary topological spaces. And if a sequence of points converges to some point X in the arbitrary Cartesian product, then if we write xn in the j tuple notation, so we will write xn as the j tuple x alpha n, alpha in j, and x as x alpha, alpha in j, then x alpha n converges to x alpha for each alpha in j. So this just means that if you have a sequence of j tuples, then each of the coordinates in the sequence gives you a sequence. So this is a sequence. This is a sequence in x alpha now, and this converges to x alpha, which is the alpha coordinate of the point of convergence x. So this is actually not very difficult, and I will leave this as an exercise. So argue by contradiction. So just let me give the hint. Argue by contradiction, and suppose that there exists such an alpha for which the coordinate sequences x and alpha do not converge to x alpha, and then you take a basis neighborhood around x alpha and arrive at a contradiction. So so I leave this as an exercise, and I will use this in the to prove that our sequence that we shall construct will not have any convergent subsequence. So what is this sequence xn? So to construct xn, note that any point in x is a function f from the unit interval to the unit interval. Now here we do not care about the topology, because this is just an index set, because remember that if you have a Cartesian product like this is exactly the set of functions from the index set to x to the union of all these x alphas, such that f of alpha belongs to x alpha for each alpha in j. This is how we defined it, in fact. And so this is the definition of the arbitrary Cartesian product. And so if each of these x alphas is the same, x alpha is the same as the unit interval, so then the union, arbitrary union is simply just the unit interval itself. And similarly j is the unit interval, okay, and therefore the arbitrary Cartesian product of x alphas, where each x alpha is the unit interval and j, the index set itself, is a unit interval, is the set of all functions from I to I. So this is the set of all functions from I to I, and let me write here f is a function, any function, and we do not care about continuity of the function or anything, because the domain in fact does not have a topology yet. So this is the set of all functions from the unit interval to itself, whether continuous or not. And so now we will use this interpretation to construct a function, rather a sequence of functions which will have no convergent subsequence. So define for each n in n the function fn, which is from the unit interval to the unit interval, and this is defined as follows. So fn of some point alpha is equal to the nth digit in the binary expansion of this number alpha. Now here we are using the concept of a binary expansion. So any number, any alpha within the interval 0 1 has a binary expansion of the form alpha is equal to let me write alpha I 2 to the power minus I equal to 1 to infinity. And so the binary expansion, so these alpha i's are in 0 1, and the binary expansion of alpha, binary expansion or base 2 expansion of alpha is just this collection of alpha i's. So alpha 1, alpha 2, and so on. So this is the binary expansion. Now notice that the binary expansion is not unique. Binary expansions are not unique in general. So why is this so? Because you can write 1, the number 1. So this has binary expansion simply as 1, okay, but this is equal to the binary expansion given by I equal to 1 to infinity 2 to the power minus I. So this is nothing but the sum of this series 1/2 plus 1/4 plus 1/8 and so on. So on the left hand side you have 1.00000 up to infinity, and on the right side you have 0 but then an infinite number of ones, and so but these two are equal, and so whenever we have this kind of ambiguity we will choose this one, choose the expansion with infinitely many zeros at the end of the expansion. So this is the only possible ambiguity, by the way. There are no other possibilities because we are just having zeros and ones. So this is the only possible ambiguity, and so in the definition of the function f, so we choose the binary expansion with infinitely many zeros. Okay, and now this gives you a well-defined function. Before, since the binary expansion are not unique, so if we do not specify this, then fn will not be well defined, but we have now chosen the binary expansion with infinitely many zeros at the end, and so now we have a well defined function fn for each n. And so now we are taking the nth digit, that the function itself takes a number alpha, so alpha belongs to 0 1, and it takes the nth digit in the binary expansion of alpha. So for example, if alpha is say 0.5, then this is nothing but half, so it will have the binary expansion 0.1, okay, and so fn will be 0 for n greater than 1 and will be 1 for n equal to 1. So this is how we define this function. So just as an example, so now we are going to show that fn does not have a convergent subsequence. So we will show that fn does not have a convergent subsequence. So why is this the case? So to show this, suppose that f and k is any subsequence of fn. Okay, so this is the sequence fn, and you have chosen any arbitrary subsequence. Now define a point alpha in 0, 1. So how do we define alpha? So we define it using the binary expansion. So the nth digit in the binary expansion of alpha is given by so it is 1 if n is equal to nk and k is even, and 0 otherwise. So we have chosen a subsequence, and with this sequence of indices nk, we have defined alpha, which has 1 in the nkth digit if k is even, and it is 0 otherwise. So let us see what is f and k alpha. So f and k alpha, so then f and k alpha is the nkth digit in the binary expansion of alpha, and this is nothing but 1 if k is even and 0 otherwise. So it oscillates between 0 and 1. Therefore, so the sequence f and k alpha, k from k in n, does not converge. Okay, so in fact we have shown that choosing any sequence, the convergence fails at some point alpha in the interval 0, 1, and this violates the lemma, and it's a contradiction to the lemma, because so this alpha can be seen as the coordinate, and we have seen that if f and k converges, then it converges at each coordinate, and we have shown that for every sequence there exists a coordinate which does not converge. Therefore we have a contradiction, and so X is not sequentially compact. We now come to the next example, which is of a sequentially compact space which is not compact, and we will again use the arbitrary Cartesian product construction here. So for this let J be an uncountable set, and we let for each alpha in J, X alpha be the 2-point set 0, 1. So X alpha is the same for all alpha, and it is the set of the points 0 and 1, and this is given the discrete topology. So X alpha is given the discrete topology, or it can also be seen, or also the subspace topology from R. So both these topologies are indeed the same because it's a finite set, and so the discrete topology and the subspace topology from R are the same. And now we are going to form again the arbitrary Cartesian product X of all these X alphas, and we will show that this is X is not compact. So again this is with the product topology, and we will show that X is not compact, but X is sequentially compact. Now X is compact by the Tikhonov's theorem. X is compact by Tikhonov's. However, we are not going to choose this space X as our space, the example that we want. We choose a subspace of this space. So define Y as a subspace of X. So this is the set of points X in X such that X alpha equals 1 for at most countably many alpha in G. So remember that X is a J tuple X alpha in J, and we in this notation we write X alpha as the alpha coordinate, and we want ones to appear in the X alpha coordinate only countably many times. So J is uncountable, but we want 1 to appear only countably many times, and the collection of these J tuples gives you the subspace Y. So Y is given the subspace topology from X, and we will show first that Y is not compact. So lemma is that Y is not compact. Now to show that it's not compact, we will show that it is not closed. Y is not closed in X. So if it is not closed, it cannot be compact. So in fact we will show that there exists a point, let's call it x0 in X, such that x0 belongs to the closure of Y minus Y. So it belongs to the closure but not inside Y, so therefore Y is not closed. So in fact we can take x0 to be the one tuple 1 alpha, the J tuple 1 alpha, which is just this is just X, so this is x0 alpha. So the alpha coordinate of X alpha is equal to 1 for all alpha in J. Now clearly x0 does not belong to Y, because since we have uncountably infinitely many ones, since x0 has uncountably many ones, so Y only consists of those J tuples which have countably many ones, and this one has uncountably many ones because J is uncountable, and therefore it does not belong to Y. However, x0 belongs to the closure of Y. So to show this, we will have to show that every basic neighborhood of x0 intersects Y. So take any basic neighborhood of x0, and so let us call this U. So U is equal to the product of all these U alphas, where U alpha is not equal to the 2-point space 0, 1, which was X alpha, for all but finitely many alpha. Finitely many alpha in G. And because U alpha is not the whole space X alpha, and U alpha contains 1 because every alpha coordinate has 1, so this means that U alpha equals the discrete open neighborhood of 1, which is the singleton set. for all but alpha equals, let's say, alpha 1, alpha 2, alpha n. So for finitely many of these it is 1, and for the rest it is of the form 0, 1. And now we can find a point in y which belongs to the intersection of u and y. So let y be defined as 1 if so y alpha is 1 if alpha is these finitely many indices that we have chosen, and 0 otherwise. Now note that we have only finitely many ones, and therefore y belongs to our space y, and also y belongs to u, because since u alpha, since 0 belongs to u alpha, which was 0, 1 for alpha not in the set alpha 1 to alpha n, and 1 belongs to u alpha, which is 1 for alpha in this index set alpha 1 to alpha n. So this means that y belongs to u intersection y, and therefore x naught is in the closure of y, and this proves that y is not compact. And in fact one can also show that remark y closure is the whole of x. So in this case we call y to be dense in x. When the closure of a subspace is the whole space, we call it to be dense, and in this case y closure is actually the entire space x, and I leave this to you as an exercise to prove. And now we will show that y is sequentially compact. So to show that y is sequentially compact, and to show this we will require some more results, and let me just state it briefly. And the theorem we need is this theorem that I stated here. So it says that if C is a countable subset of your set J which was uncountable, then this product of x alphas which is taken over the index set C rather than J, this is a metrizable space. And this result follows from the corresponding result for when each x alpha is R, and we know from a theorem in Moncrief's book, which is theorem 20.5 in my edition, which says that this countable product of R's is metrizable. And if you take the metric defined there, so Moncrief gives a specific metric which gives you the product topology and this arbitrary Cartesian product, and if you take the same metric with the same metric x, this countable product of x alphas is also going to be metrizable. So with that said, let us see why our space y is sequentially compact. So we suppose that xn n in n is a sequence in y, and define for each n the set Cn, which is the collection of indices, the points in J, such that the alpha-th coordinate of xn in this sequence is equal to 1. And we know that this is a countable set, and we let C be the union of all these Cn's, and this is countable. This is a countable union of countable sets, so it is countable union of countable sets, so it is countable. And now we choose this C to note that the arbitrary Cartesian product over X alpha, alpha in C, is metrizable, and Xn belongs to this space alpha in C, because each of these this is for all n in N, and this is because Xn can be viewed as a map from C to the union over these X alphas, where Xn alpha is equal to 1 if alpha belongs to Cn. Note that C was the union of all these Cn's, and so if alpha belongs to Cn, it is 1 and 0 otherwise. And so each Xn can be seen as a map from the union, and of course Xn alpha belongs to X alpha for each alpha in C, and therefore all these points in the sequence belong to Xn belongs to this Cartesian product over the countable set C. And notice that this is a subspace of Y. It is a compact metrizable space in Y, and therefore by the equivalence of compactness and sequential compactness, this means that Xn has a convergent subsequence Xnk in this arbitrary Cartesian product over the index set C. And because this can be viewed in Y, so what is this inclusion? So this is simply by taking any point X alpha, where alpha is in C, and we map it to X alpha, alpha in J, by simply defining X alpha to be 0 if alpha not equal to C, if alpha does not belong to C, and equal to X alpha if alpha belongs to C. Okay, so let me write it as hat on the other side. So this is Y, because you have only countably many ones, so it lands up in Y. And so Xn has a convergent sequence in this compact metrizable space of the arbitrary Cartesian product, and this is a subset of Y, and this means that Xn in Y has a convergent subsequence, and therefore we have found the criteria for Y to be sequentially compact. And with this we end the discussion of our various notions of compactness, and we will take up a new topic in the next week's lecture.